Welcome to lecture 11. Hopefully this will be a short one. We're going to be working your POGL activity, stereochemistry, and that is POGL number 7, page 80. And so we have two models here. We have model 1 and stereoisomers of thalidomide. Now, when I worked on my master's degree at the University of Louisville, I synthesized thalidomide metabolites. Metabolites are what the body converts these molecules in the liver. Thalidomide, if you look it up, it is in the 60s. It was given to pregnant women in different countries, not in the United States. The FDA did not approve, but people in Canada and Europe would take thalidomide for morning sickness. And a lot of babies were born as thalidomide babies. So what it does is it is an angiogenesis inhibitor. So it cuts off the blood flow. And so these babies were born with these underdeveloped limbs. So they would, like, their hands would come out of almost like their shoulders. And they were called thalidomide babies. And so what happens is in the placenta, where you need lots of new blood growth for the children to develop, the babies, this is prevented. Now, anyway, so it's used today. It's marketed by Celgene for an anti-cancer agent. But it was the first drug molecule that that people realized, the scientists realized, that the stereocenters create different effects in the body. Before that, nobody thought about enantiomers and publishing different enantiomers and doing studies with different enantiomers. So like albuterol, that's and it opens up your lungs, so a bronchial dilator is a medicine that opens up your airways. Albuterol is a racemic mixture, so you get an R and an S. And one enantiomer actually does the bronchial dilation, and the other enantiomer actually causes your heart to race. So there is another isomer of albuterol in its class, but it's just the isomer. But it's not as effective or strong, but a lot of times you give that to babies because it doesn't cause the heart racing. So now, because of thalidomide, studies are shown and done on both enantiomers. Okay, and that's what we're talking about here. So one of the following compounds is thalidomide. So we have compound A and B, and we have some definitions. So you can see that on page 80. So let's just go ahead with the questions. Q1. Do compounds D and A have the same molecular formula? So same molecular formula, yes or no? C13H10N2O4. Did you say yes? Okay. A and B are, okay, so the same formula. Are they the same molecule? So are they constitutional or conformational? Constitutional isomers. Constitutional isomers have same molecular formula, but different connectivity. Conformational isomers are like the chair, okay? So what's different? This is connected here, so we have the carbonyl. This is actually the imide. It's called an imide, with the nitrogen between two carbonyls. So that's 1, 2 here. 1, here we got a methylene in between the imide. So you see how it's different connectivity, okay? It's constitutional. Number 3, put an asterisk, this is an asterisk, make it blue, next to any carbons that have 4 different groups. What term is used to identify this type of carbon? Okay, we called it an asymmetric carbon, didn't we? Okay, asymmetric. It's also called a stereocarbon. What do they call it here? They call it a chiral carbon. Okay, a chiral carbon. Do they do a chiral center? Okay, so they call it a chiral center. So let's look at the different carbons. So these carbons are all double bonded. Okay, so each one of these are sp2 carbons. This carbon's bonded to 2 oxygens, so that's not a stereocenter. Okay, and nitrogen. This carbon is a CH2, and this carbon's a CH2, so that's bonded to the same thing. Do you see how this carbon is your stereoisomer? It's bonded to a nitrogen. It's bonded to a carbon that's a carbonyl. It's bonded to a CH2, and then what's not shown there is a hydrogen. Okay, so we can draw that hydrogen in there. Over here, we do not have an asymmetric carbon. So if you look at this carbon here, it's bonded to a nitrogen, which is different. It's bonded to a hydrogen, but you got to do CH2, CH2 is the same. Then you come up here and you say carbonyl, carbonyl is the same, and then I always do this with my fingers, we meet to the nitrogen. We meet, our fingers go around the ring and they meet. So you do here, that's the same, you go here, same, and then they meet on the NH. So there's not a point of differentiality, okay? So this is going to be a plane of symmetry. So that's what 4 is asking. Determine if there is an internal plane of symmetry in compound A or B. And draw a dotted line to determine where the plane is. So you see where I drew the dotted line? Okay. Number 5, based on your answer to number 4, which of the above structures are a chiral compound? So A is a chiral compound. And that would mean this compound is achiral, okay, because there's a plane of symmetry. Number 6, question number 6. Which of the above structures are achiral? So the answer is B. Thalidomide is a chiral compound. Which structure is thalidomide? Thalidomide is compound A. Okay. Using wedges and dash structures at the chirality center, draw 2 stereoisomers of thalidomide. All right, so I'm going to do this and you can do it, and we just all do it together. All right. So I like to draw them like this, because this is how I would always draw my thalidomide structures. And here's your nitrogen. Okay, and I'll just do the same thing here. There's your image. And then you have this. All right, we can make this one a wedge. Put the dash in back. Make this a dash, and then the wedge would be hydrogen. To my hydrogen. And you don't even have to put your hydrogen in, but you do need to have one of these is the wedge and the other one's the dash. Okay, question number 9. The chirality center and 4 adjacent atoms have been extracted from thalidomide to give a simplified structure below. You can use your model kit and make that if you have a model kit. Confirm that they can be superimposed onto one another. Okay, so we're just going to go on to 10, since we don't really have our model kids out here and we're not in class. Switch any two groups in one of the models and leave the other one unchanged. Okay, so like I said, that would be in class. Um, which definition, let's do 10b. Which definition from the following list best describes relationships between the two models? So if you made these two models and saw that these were mirror images of each other and they're non-superimposable, what would that be? An enantiomer. Is the molecule chiral? Yes. There is only one chiral carbon, no plane of symmetry. So if you have one chiral carbon or asymmetric carbon and there's no plane of symmetry, okay, it's going to definitely be a chiral molecule. All right. Let's just go ahead. Well, we'll go to the next model. Let's do the next model. Okay, model 2. Now we're going to talk about chiral centers R and S. And so you can go ahead and start answering the questions as I draw the models here. And then we can come together. So this is a 3, a 2, okay. Um, Now you'll see I do mine very quick. So if you listen to the other lecture, so we're going to go through this because I think Pogel does a good job, but then I'm going to tell you my quick way of doing this. I don't actually redraw these molecules, okay? So let's do 11. Once the chiral center is identified, groups are prioritized. So we have to assign priority. And there's a lecture about how to do that. 1 is the highest, and 4 is the lowest. And it's based on your atomic weight or your atomic number. Which group in Model 2 has the highest priority? And you're supposed to circle. So bromine has the highest, and if you look at your periodic table, it has an atomic number of 35. Which in the group has the lowest priority? Did you choose hydrogen? Atomic number 1. Which atom from the group has the highest atomic number? Bromine, 35. Which atom from the group has the lowest atomic number? Hydrogen. What conclusions can be made about priority ranking and atomic number? So what did you write? The higher the atomic number, the higher the priority. Therefore, gets assigned a number 1. And then you go from there. Okay, number 12. To prioritize groups that have the same atom. In this case, the group are carbon. Compare the next 3 groups connected to each carbon. This is illustrated using a tree diagram. So I'm going to draw this out. If you want to, you're welcome to go ahead and answer some of those questions on your own. Okay, so we have 4 atoms connected to a chiral carbon. There's your chiral carbon. And over here, we have a tree diagram showing 3 additional atoms connected to the carbons. Okay, so here's your chiral carbon. Here's your bromine. And then here we have this carbon, we have this carbon, and this carbon. All right, so 12A. The 4 atoms connected to the chiral carbon are drawn on the left. Label the highest priority group 1 and the lowest. So did you make bromine 1, hydrogen 2, right? This is 1. This is, oh, I'm sorry, not 2. The lowest priority, 4. There's your lowest, is 4. Okay, so it's to label the highest priority group 1 and the lowest priority group 4. All right, since the two groups are a tie, the tree diagram shows that what is bonded to each carbon. So if you notice, this is a carbon and this is a carbon. And so we made a tree diagram. For the methyl group, the 3 atoms connected are hydrogens. Okay, so now we're looking at hydrogens. 3 hydrogens. For the ethyl group, the 3 atoms connected to the carbon are 1 carbon and 2 hydrogens. Compare these 3 atoms for each group. At the first point of difference, the group with the highest atomic number gets the higher priority. On the structure, label which groups get the priority 2 and 3. Okay, so the carbon that's connected to another carbon is going to get number 2. And then this carbon is just connected to hydrogen, so it gets 3. Okay, number 13. Once the priority of the groups have been established, the lowest ranking group must be oriented back or away from your perspective. In Model 2, so we're looking at Model 2 here. This is our Model 2. In Model 2, the molecule has been flipped to accomplish this. Next, trace a pathway from 1 to 2 to 3. Okay, so this molecule, you see the beginning one, the hydrogen's in front. Okay, so what Pogel's doing is just flipping, so the hydrogen's now in backs. And when you flip that, you call it a flip, but it's a rotate. Okay, you rotate it 180 degrees. So you take this molecule and you rotate it 180 degrees. Remember, whenever you rotate, okay, what is on the left, so this ethyl becomes on the right. So this is left, the CH3 stays up front, so that's why it's not really a flip. And then, so the left, that becomes a right. And what is away from you, what's on the dash, becomes the wedge. Okay, and so now we do our assignment here. So this is 1. This is 4, this is the ethyl's 2, and the methyl's 3. And then we connect our 1, 2, 3. And so what is that? If you turn the steering wheel, that would be counterclockwise or left, which is S. This is S. Okay? So that answers 13. Now what I do, just so you know, I don't actually take the time to draw this redraw because I don't necessarily have the time to redraw. What I do is I just do the connect, I assign my priorities, then I connect 1, 2, and 3. Okay, so I do connect 1, 2, and 3, and I say, okay, that is what? R. And then I check, is my lowest priority in back? And the answer in this case, hydrogen's coming at me, okay? So no. So I do a switcheroo. So I would take R and I would just switch it to S. And I would say this molecule is S. But see how over here they redrew it and worked on this one? The answer is still S. Okay, so you can do it either way as long as you get the right answer. All right, so we're on number 14. It says to rank each substituent on the chirality center of the molecule from high priority 1 to low priority. If the priority cannot be determined based on the 4 atoms, draw out tree diagrams. Okay, hint, a double bond counts as being bonded to 2 of the same atoms. All right, sometimes you'll get questions on your assessments that just ask you about priorities, and you will have homework on your sapling. So by assigning priorities. All right, so here we have this, and let's assign our priorities. So hydrogen's easy, right? Because its atomic number is 1, so that's 4. That's your lowest priority. And then we're comparing nitrogen, carbon, and a carbon. Well, nitrogen is atomic number 7, where carbon is a number 6. So what's our highest priority? The nitrogen would be 1. Now it says we've got a tie between the 2 carbons. So Pogel wants us to draw a tree diagram. So this is what they're wanting you to draw. Where you just basically draw all of these out. And you see, so now we're comparing the carbon versus the carbon. So this is our 4, this is our 1. So this carbon is bonded to 3 hydrogens. This carbon is bonded to 2 oxygens. See how you make your double bond, bonded out to 2 things? Okay, so yes, so number 2 would go to what I call the carbonyl, and number 3 would go to the methyl. All right, now I don't do B and redraw. Okay, so this is where on number 14, I'm just going to do it the way I do it. So we've assigned our priorities. Now we connect the 1, 2, 3. Okay, so when we connect the 1, 2, 3, what is that? You're turning the wheel to the right. All right, so that's R. Now, then you do your is number 4 in back. It's not, is it? No. So do a switcheroo. So R becomes S. So the answer here is S. So this stereo center is an S configuration. Indicate which pathway from high priority to low priority. Okay. So here it's clockwise, but then you do the switcheroo. The answer is S enantiomer, so that's D. 14D. All right, so let's do 15, and then you will have your additional problems to do. Okay, for the following steps listed above, determine the absolute configuration of each of the chirality centers in the compounds below. Now, if we were in class, I would ask each of you in your groups to go to the board. I would have these molecules drawn, and then people would work these on the board. So as you're listening to these and working your problems, just try to feel like you're not alone. We have 25 students in this class, and each one of you are working these problems. Okay. We're assigning priority. All right. Did I draw them all correctly? Okay, so here we have these molecules. All right. So we have to find the chiral center. So here's your chiral center in A. Everything else is not. I mean, because you look at this carbon, even though that's a CH, bond to CH3, CH3. That's the same thing. Okay, so let's assign priorities. Which one's 4? Hydrogen, right? Which one's 1? Oxygen, right? And then we have a carbon and a carbon. This carbon is bonded to 2 carbons, is bonded to 3 hydrogens. So which one's 2? This would be 2, and then this would be 3. Okay, so we assign our priorities, and then we connect the 1, 2, 3. 1, 2, 3. So you're turning the steering wheel to the left, right? So that's S. Now do your check. Is the lowest priority in back? Now this is easy to do when you have it on the dash or the wedge to answer yes or no. But what if you have it on the plane? So what you have to do, if you have a molecule, we'd have a molecule in class and everybody would make it, you hold on, you put your hand on that bond and you turn it to your eyeball. So your eyeball is here, okay, and you're looking there where hydrogen's in the back. And then you connect your 1, 2, 3. If you do that, you have to go back here, 1, 2, 3, and you see that S stays S because hydrogen is in back. Okay, so that one should be S. And if you have to, make a model of these. Because, I mean, the nice thing is you can make models while you're taking your assessments. You're kind of doing this all at home. All right, once again, B, there's your stereocenter. Nothing else is a stereocenter because these are sp2 carbons, cannot be. So this is your stereocenter. Yeah, that's your asymmetric carbon. Okay, where's number 4? Your lowest priority is hydrogen. Your highest priority would be bromine. And then we have a carbon and a carbon. But this is a CH3, and this is a carbon essentially bonded 1, 2, 3 carbons. So this is bonded to 3 hydrogens. Okay, so which one's going to be 2? And which one's going to be 3? All right, now we're going to connect them. 1, 2, 3. 1, 2, 3. You're turning the steering wheel clockwise or right, so that's R. Does is your lowest priority in back? And this one's easier because you see it's the dash. So yes. So R stays R. So that one's R. Okay, here's a cyclic compound. Once again, you might want to make a model. Your stereocenter is here. Okay, the other carbons, this is a CH2, CH2. This is a carbon sp2 bonded to 2 carbons, same thing here, and this is CH3. So this is your only stereocenter. And if you want to, you can go ahead and draw what's not shown here. If this is coming at you, hydrogen then back. So hydrogen is number 4, and oxygen is number 1. So what's number 2? Well, you have this carbon that's bonded to 1 carbon. This carbon is bonded to 2 carbons. So this would be 2, and this would be number 3. So if you have this molecule and you're holding hydrogen in back, 1, 2, 3, you connect the 1, 2, 3, you see that that is S, and the hydrogen is in back. So S stays S. Okay. It looks like you have additional problem 16. And you can make models of those. That would be good. Some of these are actually kind of hard. I can go ahead and tell you A has a plane of symmetry. Okay. And the way you'll do that, let me go ahead and show you that. Excuse me. So we have CH3 here and OH down here. So you would want to say, okay, is that carbon is bonded to this CH3 and this OH, but you go out here and you're saying, see the green and the blue, they're the same. They're both CH2s. So you go to the next one. CH2, CH2, those are the same because you keep working out to see if there's something different. And then your fingers meet. If you have one finger here and one finger there, they both meet, right? So if your fingers move and meet, if you meet, see, then you basically say this is not an asymmetric carbon. Okay, and essentially it has a plane of symmetry, and so this would be molecule is a chiral. So if you have a plane of symmetry, you can also look at the next one. What do you have here? You have a methyl here, hydrogen there, methyl here, and a hydrogen there. And you see that this is a plane of symmetry. Okay. If you do have chiral centers, then you need to decide whether they're R or S. Now, the other two examples you have there, C and D, I will tell you between C and D, one is chiral and one is achiral. So see if you can see which one's chiral and which one's achiral. And so you only have one chiral compound for 16 to do R and S. It looks like all of compound 17 are chiral. So you can assign priorities and work those. 18, they have you to redraw and swap them out. You don't have to do that for 18. If you want, you can just do it the way I do it in the previous lecture, where you just draw the molecule and you assign priorities and you determine whether it's R or S, whether you have to do the switcheroo or not. Same thing with 19. Assign your priorities, do the connect 1, 2, 3, and then decide whether it's R and S. 20, you have to find which one are stereocenters. Okay?